Wait for it. Well, I want to start by thanking the organizers for organizing this wonderful school and well, giving me a chance to come back here after many years. Okay, so I was tasked to talk about holography. Of course, it's a vast subject. It sort of refers to this original paper by Maldacena, by and large, and that has since 25 years, it has about 18,000 citations. So of course, I'm not going to do any justice to even touching, the main aspects of this vast subject. But what I want to focus on, since this is a school on gravity after all, is sort of the gravitational aspects of holography. And what in particular I'll try to do is to sort of give you some feeling of using GR tools in a context where you can learn something about non-gravitational physics, for example, and vice versa, eventually bootstrap to learning something about quantum gravity. So you can take this as a sort of an applied course in global structure of space-time. But to build up to that, I will first try to contextualize holography. So in this lecture, I'll talk about the sort of the motivation or the construction from sort of the string theory context of this correspondence. And maybe we'll, depending on how things go, I might get to talk about the anti-de Sitter space-time, just the geometry of it. And then we'll see how things go later on. I haven't really planned much concrete stuff, so I will welcome your feedback to see whether I should speed up or slow down, whether you want to hear more about some specific aspect and so forth. Okay, so we can play it dynamically. Okay, so here I have put a few references. There are tons of references, and in fact, there are tons of summer school lectures on ADS-CFT. There must be hundreds of hours that you can listen to of excellent lectures. So I'll try to give this in some sort of a complementary fashion of sort of trying to give you my intuition or insight, sort of slightly pictorial version to just at least get a conceptual grounding in what the physics is saying. So this review by Aharoni and company came out very soon afterwards, but the rest of these are more in the sort of a gravitational context. After the first three, I sort of jumped by a decade. This was a review for TASI summer school lectures. And then I will model the first part of the lecture on the review that I wrote for Einstein centenary, where one of the milestones of GR after its first century was deemed to be the ADS-CFT. So this was written for a GR audience, but there are many reviews, and there are further reviews referenced in these. Okay, so let me start with a philosophical sort of introduction, which is to try to emphasize that, in fact, black holes provide a sort of a crucial role, or key role to play, in fact, at many layers, at many levels. So one thing that we heard earlier, which was sort of you can think of as a prequel to the ADS-CFT, is the black hole thermodynamics. So you know that the entropy of a black hole is given by the area of the event horizon over 4 in Planck units. So actually, it's sort of cute if you reinstate in the constants of nature to write it instead of setting all of them to 1. Well, you have, of course, Boltzmann constant, you have the speed of light, and you have the Newton's constant, and Planck's constant. So all of these, so you can think of, understanding this at some deep level really requires knowing, statistical mechanics, relativity, gravity, and quantum mechanics. So this is one of the sort of, to me, very nice formulas in physics. But what does it say? The entropy is given not extensively in volume, but rather as a surface area. So this actually generalizes to, well, what eventually became known, or well, as a speculation or expectation, as sort of the holographic principle. Which, roughly speaking, it's based, so this word holography is the reason for this word holography. It's motivated by acknowledging that somehow you can describe physics in some number of dimensions by a lower dimensional description. And in particular, it's a feature of any theory of Einstein's theory of gravity with a requisite energy condition. And roughly speaking, it just says that if you have any spatial region, so let's take in space-time, so where this is time, let's take some codimension 2 surface. So let's say in our space, we take some sphere, and we ask how much can I pack in the sphere, or more precisely, what is the entropy? Now, I want to define this in some sensible way covariantly, so I don't want to just say, well, what's the volume inside the sphere, but if you do it covariantly, a la Raphael Busso, you can say, well, take a null normal congruence to this surface. Well, and you want to take a congruence such that it's locally converging everywhere. So such a congruence, if it has converging null normal rays, is called a light sheet. And, well, in flat space, if you have, let's say, a sort of spherical region, it would cover up all of this. And the statement is that the entropy that passes through this light sheet is bounded from above by area, quarter of the area of the surface. Okay, so it's mimicking this physics that somehow you can't pack more entropy in here than given by a surface area rather than volume. Okay, so here we see this loss of extensivity. Now, physically, you might say, well, okay, if I can pack some amount of information in this room, well, I should be able to pack twice the information in, twice the size of this room, so why isn't it extensive? The thing that intuition ignores is gravity. Once you pack in sufficiently, well, have sufficiently many rooms, or pack in sufficiently much information in this room, the whole thing will collapse into a black hole, and then we're stuck with having this entropy scaling with a surface area rather than the volume. Okay, so this is this sort of entropy bound scaling with the area rather than volume is just a feature of gravity, of Einstein's gravity. And the holographic principle elevates that to speculating that, well, if you can not fit more than surface areas worth of information, well, then maybe there is an autonomous theory on the surface that describes all this physics. Okay, so that's the only concrete example we have of that, where we can actually describe this in full, but not full, but exquisite detail, is the ADS-CFT. But nevertheless, that was sort of the motivation. That's the motivation for why we're thinking of this as holography. Okay, so black holes led to sort of understanding this feature, but once you have entropy as a thermodynamic object, we're used to thinking of it as, in statistical, mechanical setting as describing or being related to sort of the number of microstates. And so there was a big program in terms of trying to explain this from first principles. And this black hole sort of microstate counting, was studied very extensively in string theory, superstring theory, which, well, so string theory, by the way, is a rather a misnomer. First of all, it's not just about strings, and second of all, it's more a framework than a theory, but never mind. The content of it, so it has strings, it also has other objects like d-branes and so forth. And studying how these objects behave, and in particular, how many ways you can excite them in at when the strength of interactions is weak, can be related in certain regimes to how many microstates you have for a black hole that has the same charges as this configuration in string theory. So this provided a framework to counting the black hole microstates, and indeed we reproduce this in sufficiently super near sort of supersymmetric regimes or set of black holes, not our favorite Schwarzschild black hole, but many other ones. And in the process, we sort of learned more about the behavior of the objects in this. And learning about the behavior of objects in this eventually led, and this is what I'll talk about in a moment, led to this ADS formulation of this ADS-CFT correspondence. So we'll see this in a moment. But I want to stress that black holes played a role in formulating this through trying to sort of understand, along sort of many years of development, but I think this was the black holes were at sort of heart of this. Now, once you have the correspondence, it's a correspondence between a theory of gravity and a non-gravitational theory. And the theory of gravity has all the gravitational effects we're familiar with. In particular, you can take stuff and collapse it into a black hole. So it has black holes. In fact, it has black holes as very prominent, typical configurations in such a theory. So you can think about black holes within ADS-CFT as giving us sort of a very good, let's see, this is the back, very good playground for quantum gravity. So this is sort of, they provide a playground for understanding quantum gravity, but they also, well, and they also sort of are at the heart of understanding sort of the dictionary between the two sides, which, again, that's much of what I'll focus on in the first part of the lectures. But at the same time, describing some gravitational physics in terms of non-gravitational one, then suggests that there will be non-gravitational systems which are described by black holes. So you might find it's quite remarkable that this is sort of, it means that studying GR is really relevant not just to astrophysics and cosmology, but to pretty much everyday world. You might study conformal fluids, say quark-gluon plasma or cold atom systems or things like that we can produce in our lab, where gravity plays very negligible role. And it's remarkable to think that such a non-gravitating system should have anything to do with being described by a theory of gravity, especially by the most gravitational systems possible, namely black holes, and yet that's precisely what we're finding. So we're finding that that black holes in sort of higher dimensions describe very efficiently non-gravitational, sort of everyday, almost everyday systems. So I find this very remarkable, but that's sort of the that's the lesson that we have been learning. And moreover, we have been learning that black holes are somehow very intimately connected to, in some mysterious fashion, so far to quantum information, or manifest the connection between sort of space-time and entanglement and so forth. So maybe towards the end of the lectures, I might try to give you a little bit more, insight into what is meant by that. Okay, so that was just a very broad introduction. So let me now get more to the heart of the matter and sort of try to sketch out a derivation of ADS-CFT from the context of string theory. Okay, so let me just put this all the way up. Okay, and then I can bring this one down. Now I got stuck. Okay, never mind. You can see the top, right? Oh, I see. Okay, fine. So thank you. So you can bring it down. Actually, I need this one. Bring this one down first so that I can start writing. Yeah, that's good. Okay. So this is derivation in quotes. I'm very schematic here, but just to motivate where it's coming from. So you take a sort of string theory, which naturally is lives in 10 dimensions, 9 plus 1 dimensions, and you consider a certain system in it, a so-called a D3 brane. Okay, D brane is a Dirichlet brane. It's something that provides boundary conditions for open strings. So we can have open string ending on this D brane. The 3 refers to that it's 3 plus 1 dimensional world volume. And you take n of such D3 branes, a stack of n of these D3 branes that are, okay, I'm drawing them as slightly separated, but really you should think of them as all lying on top of each other. Okay, so there are n of these. And you can have these open strings that sort of start on one and end on another, and so forth. And you also have closed strings propagating in the bulk. And in string theory, the strength of interactions of these strings, how they can split and join and split, is governed by the string constant, G. And the mass of these D branes goes as inversely with this string coupling, but the amount of back reaction is Newton's constant times the mass, and Newton's constant scales as string coupling squared. So the back reaction, amount of back reaction of these D branes on the geometry is governed by the string coupling G times the number of these branes that I have. So when I have G string n very small, then you can think of this configuration as just a bunch of branes in nearly flat spacetime. But when you have the coupling large, so G n much bigger than 1, the back reaction is large, and these things back react on the spacetime. Now, these objects are supersymmetric, so they're like analogs of extremal Reissner-Nordström black hole, except that instead of having a point-like, spatially point-like, compact source, you have a 3 plus 1 dimensional world volume of these things. So the metric in 10 dimensions will look very analogous to the Reisner-Nordström, but now you have all these extra directions. So what does it look like? So first of all, you have I can again sort of write this as, let's say, a parameter R that takes me away from these D branes, and I can write a sort of embedding diagram type picture where, so here we have R going to infinity far away from the branes. It's asymptotically flat. Now, as you go towards the brain, as R goes to 0, you go down infinitely deep down the throat. That's where the horizon will be. So now, if I write the metric, so this will be sort of extremal black brain geometry. So in coordinates which are sort of analogous to the Majumdar-Papapetrou, but with single center coordinates, we will have something like this. So we have, I'll leave a space, there will be a prefactor multiplying the world volume. The world volume is just flat, so eta mu nu dx mu dx nu. And then there will be a prefactor of this, which I'll write in a moment, and then another prefactor times the transverse space. The transverse space is the usual dr squared plus r squared, the omega squared. But now, so this is a metric of a sphere. How many dimensions does it have? Well, since the whole space-time has 10 dimensions, here this is just 4-dimensional. So this must be 6-dimensional, so there's a 5-sphere. And the prefactor there can be only function of r. So there will be, let me write it as f of r to minus 1/2, and f of r, well, 1 over this, so to 1/2, where f of r is 1 plus some constant, let me call it L, to the 4th over R to the 4th. The 4th just comes again from the dimensionality of this transverse space. And this constant L is written, well, let me write it as L to the 4th. In terms of the parameters of the problem, it's given by some number, 4 pi times the strength of this back reaction in string units. Okay, so this is the string length, sort of a fundamental length scale in string theory. Okay, for our purposes, that doesn't really matter, apart from if you fix the string scale, then this number governs the size of this parameter here. Otherwise, it's just nice asymptotically flat geometry, which has a horizon where, so again, comparing with the Reisner-Nordström, right, this would be just dt squared, because you don't have any extra spatial dimensions to the black hole. Here we have 3 extra spatial dimensions, but this prefactor vanishing gives you the horizon, and the prefactor vanishing gives you, happens at r equal to 0, because this goes to infinity and 1 over square root of that goes to 0. Okay, so the horizon is at r equal to 0, which has a coordinate singularity, just like the Majumdar-Papapetrou coordinates did, but that's okay, you can go through that. And, well, there's a scri plus, because it's still asymptotically flat. Okay, this is not a very good way of writing it, but basically it's a good infinite r and infinite whatever else you need. Okay, so out there. And you can also see now, as you go near the horizon, okay, this factor you can ignore, but as you go near the horizon, 1 over square root of f of r has this 1 over r squared, so there's an infinite distance to get to the horizon. So in this direction, it takes infinite distance. So you have this infinite throat. Unlike for Schwarzschild, the embedding diagram would have flared out at some finite distance like this. Here, it just goes on forever before you get to the horizon. Same as for extremal Reisner-Nordström. Okay, there was a question. Was there a question?
That shell is just horizon radius has something to do with brain length.
L has to do with, well, how strong the string coupling is and how many branes you have. So how much back reaction there is. So the larger this number, the bigger horizon this is going to produce. So it sets the scale. It sets the scale by what we fix the parameters to be. So you can take N and G as sort of free parameters. And we're now looking at this configuration at various values. The relevant one is the product of them, Gn, and we're now looking at the various regimes of Gn. Does that answer it? Okay. Any other questions? Yeah?
S is related to the alpha-prime parameter also?
That's right, exactly. Just by factor square root. Okay, good. All right, so that's the geometry. Now, of course, if you plug that into Einstein's equations, you'll find this is not satisfying the vacuum Einstein's equations. There's a stress tensor. It's supported, so this metric has a stress tensor that corresponds to a generalization of the Maxwell field. In this case, in this geometry, it's a self-dual 5-form field strength. Let me just write it schematically as F5, which has flux through this 5-sphere. You don't really have to worry about the details of that, but okay, that's a solution of the system of equations. And now, notice we have been talking about two regimes, which a priori are completely separate. So far there isn't any connection between the physics at weak coupling and physics at strong coupling. But now we'll do a trick. The trick we'll do is to take a low energy limit Okay, so in the low energy limit, on this side, what happens is that the closed strings decouple, and you end up with a theory of just open strings tugging on this system of D branes, and that corresponds to a Yang-Mills world volume theory on the brane. Effectively, these strings tugging on it, it's like modes of the fluctuation modes of the branes, and it's described by this theory. So in the weak coupling, we get a super Yang-Mills theory with a gauge group. It's a 4D because it lives on the world volume. It's still going to be maximally supersymmetric, and it's a gauge theory with gauge group SUN. This N now is the rank of the gauge group. That's the number of these D branes. In this regime, what happens is to take a low energy limit, you go down this gravitational potential well, as it were. You go to the near horizon geometry. So you take near horizon geometry, which means you're capping off this asymptotic region. You're down in this throat, and you have an enhanced symmetry because now everything has this, the throat keeps looking the same all the way down. So that's the near horizon geometry. Near horizon geometry. And what is that? Okay, this is too low for me. What are we? Oh, that's the middle one. Okay. There is still some space in the other room, so let me utilize that. Okay. So near horizon geometry corresponds to the limit r equal to 0. So when you do that, that means that f of r goes to just L to the 4th over R to the 4th. And so here, what happens to the metric? You have inverse of the square root of that, so R to the 4th, R squared over L squared times our flat 4-dimensional Minkowski metric, plus here we have L squared over R squared with the dr squared. And then we have L squared over R squared times R squared. So this is just L squared, d omega phi squared. And so this is just a product of a sphere, of a phi sphere of size L, and 5-dimensional ADS. So this is ADS 5 times S5, both having a characteristic scale, which we'll call radius L. Okay, so the ADS spacetime comes out from this near horizon geometry. So if you did this exercise for the Reissner-Nordstrom, extremal Reissner-Nordstrom black hole that Malcolm was telling us about yesterday, you would find ADS 2 cross S2. Now it's the same thing, it's just in higher dimensions. Okay, and ADS is infinite space, but it has a scale set by the curvature. It's a negatively, maximally symmetric space of constant negative curvature, which is set by the scale L. It behaves like a confining box. So if you take, say, time-like geodesics, they slosh around in ADS with period, again, proportional to L, 2 pi L or something like that. Okay, so L is, in that sense, the characteristic size or radius of ADS. Okay, so we started with 2 different regimes. We took low energy limit, but now this thing is defined, well defined for any GN, and so in particular we can extend this from the to have an overlapping regime of validity. Okay, and so that leads to the, well, at Maldacena, to the formulation of the ADS CFT. Okay, now this will take a while. I want to get the front one down. And I want to nudge the other 2 up. While all that is happening, feel free to shout out questions. Yeah?
In what sense is it a low energy limit when you go near the horizon? Sorry, can you please repeat the question so that they can hear?
Good. In what sense is it a low energy limit? Well, in what sense do you go near the horizon in order to take the low energy limit? So you can think of the, again, if you want in sort of Newtonian intuition, you're down this gravitational potential well. So you want to go deep down the throat, and that is going near the horizon. Okay, that's the most pedestrian way of thinking about it. You can also, well, maybe let me just leave it at that if you're happy with it.
It's like energy as
You can think of the energy of, say, probes of the geometry, and you can see what part of the geometry they're sensitive to, for example. And then you recover the near horizon. Or better yet, take it from the other side. If you're trying to climb out of the near horizon region, you really redshift it to get out. So the near horizon region is the low energy one. Okay. Yeah?
How is the near horizon region R tends to 0? It's not R tends to L.
Well, the sphere, it's smeared out. Okay, so I gather the question is asking what role does the sphere play, roughly speaking, or?
You put the near horizon condition is R tends to 0. It's not R tends to L. You said the L is the horizon.
L sets the scale. So like the scale of curvature for the spacetime. Okay, now, if you look at the metric, look at that metric, where is the horizon? The horizon, so it's a static metric, it's a static geometry. And so we can very easily find the horizon not as an event horizon from sort of the global structure, but just as a killing horizon. Okay, so this is where the killing field ddt, or in this case dd x0, becomes null. When does it become null? It becomes null when 1 over square root of f of r becomes 0. When does that happen? From the form of f of r, that happens when r is 0. I mean, you can think of it as r over L is 0 to deal with dimensionless quantities, but anyway, it's the same thing. Okay, so you have, if you want, r divided by L going to 0. Okay. Other questions? Yeah.
I'm a little confused about charges of the theory, because I expect that you have some kind of mass or something like that, and when you do this low energy limit, I would say that it corresponds to taking a limit like mass is going to 0 or something like that. And you have nothing like that in your theory.
Well, okay, so this is more tricky because we're going to, you see now we're no longer in asymptotically flat space-time. We have dropped the, ADM mass computed at infinity. We're now looking at a different geometry. But what is true is that it's still, it retains the, well, it has now enhanced symmetry. But the charge, the analog of the electromagnetic charge in this case is still the same. The flux through the, so now the brain, okay, so maybe one should ask this way. What happened to the brains? What happened, so maybe you're all sort of driving at that. What happened to the brains when we took this low energy limit? We went to the near horizon geometry. The brains sourced the geometry that had a horizon, but what happens to the brains? Well, they're no longer apparent in the theory as localized objects anywhere, because we just went to this near horizon limit of the geometry, but their origins are still present by still having this 5-form field strength flux through the 5-sphere. Okay, so it's still not a vacuum solution. It still has the same charge, but now we have zoomed in onto it. And indeed, now the brains have sort of dissolved into this flux, but the flux is still there, and you can view this configuration in 2 different ways. You can think of it as really a non-vacuum solution with 0 cosmological constant, or you can dimensionally reduce on the 5-sphere, forget about the flux, and think of this just as a ADS5 geometry. So that's a solution of vacuum Einstein's equations with negative cosmological constant. And for many purposes, depending on what you want to do, that suffices. So you can think of, just this ADS5 geometry, or you can, if whatever is happening in this sphere is sort of trivial, you just smeared over the entire 5-sphere trivial, you can just forget about the 5-sphere. At the expense of doing physics with negative cosmological constant. Okay, so hopefully that, thank you for the question. Any other? Okay, my time, okay, I have 20 minutes, right? Okay. Good. Okay, so, good. So now that motivated the formulation of the ADS-CFT correspondence, which then says that this string theory, a specific type of the string theory, don't worry about that, on this ADS5 cross S5 geometry is dual, meaning physically equivalent, describing the same physics in completely different language, but the identical physics, to a 4-dimensional supersymmetric, so it has the maximum number of supercharges. Again, don't worry about that, but just to be complete, Super-Yang-Mills theory, which in some sense can be thought of as living on the boundary of this ADS5. Okay, I'll say that a little bit more in detail in a bit later. And so now I'll make a bunch of remarks about this before sort of trying to delve into, how do we make sense of it. Okay, so one thing to say is that, well, string theory, of course, contains gravity. So we have a theory of gravity. This is a non-gravitational gauge theory, meaning it doesn't manifest gravity. It's a gauge theory, and in particular, it's one which is conformal, so it's a conformal field theory. And so here, this name ADS-CFT harks to the fact that this gravity theory lives in ADS, and ADS times S, and it's dual to this conformal field theory. Now, here, because we have gravity, we can have, as I said, we can have excitations above just this maximally symmetric space-time. We can have black holes, we can have gravitational waves, we can have whatnot, whatever system we want to consider. And so this is really asymptotically ADS5 cross S5 rather than the exact thing. So exciting, well, the vacuum state in this theory corresponds to precisely this geometry. Once you sufficiently excite this to some highly excited state, then that corresponds to some geometry that only asymptotes to this one. Okay, so we'll gradually start to consider this more general context because that's much more fun. But for today, I'll remain in just this pure ADS, and maybe even won't get to that, we'll see. But let me sort of now specify a little bit more of what is the regime for these branes and so forth that we're looking at. Okay, so we have on this side, we have two dimensionless parameters that we identified. One is the string coupling, and one, if I wanted to do it dimensionless, we have this scale for the size of ADS, which is L, but that's dimension full. What we want is to take it in some units. So in string theory, the natural thing is that size of ADS in strings units. Okay, so those are two parameters. Here we have the rank of the gauge group, this SUN, and we also have a coupling, which is most naturally expressed as a 't Hooft coupling. So this is coupling, which is defined as the Yang-Mills coupling squared times n, okay? And there's a match between these two pairs of parameters. The match is the following. So we have the string scale is given by, well, 4 pi times the string scale, which is the Yang-Mills coupling squared, is just this lambda over n. And the size of ADS in string units is given by, well, from the definition up there, well, it's this 4 pi gn to the 1/4. But what is that? Well, that is just the 't Hooft coupling to the 1/4. So what do we want if we want to describe, if we want to play with just classical gravity in the bulk? We want the stringy corrections to be small. So, string theory has this extended object strings. We want to not worry about sort of physics happenings and happening and that's sensitive to that scale. So we want suppress stringy corrections to classical gravity or Einstein gravity. We want to have L very much larger than the string size. Okay, so Hoof coupling has to be very large, but at the same time, to suppress quantum corrections, and this G really tells us how strongly the strings interact. So to suppress, to tame this interaction, to suppress quantum corrections, we want this G to be very small. So it's weakly coupled. And so that means lambda has to be very large, but lambda over n has to be very small. And so we get to the regime that you have all of these scales separated. And in this regime, we get just classical gravity in the bulk. In bulk, meaning in ADS. So that's the regime that we'll be playing with in these lectures because, after all, well, I'm going to focus on just classical Einstein gravity. You can, of course, formulate, well, and this is the regime where we have the strongest, the best control over what's happening in ADS-CFT. We have lots of handle on what's happening perturbatively in 1 over lambda and 1 over n. And it's much more at the conjectural level that the duality holds at finite lambda and finite n as well. But there it's very hard to get the machinery, the toolkit, to actually check things explicitly. Okay, so anyway, so that's the regime we'll be focusing on. And so let me now make bunch of remarks. Okay, let me just first start here. Okay, go for it. Good. Yes. Okay, that's a very, the short answer is yes, but let me, okay, let me postpone that because that I don't want to get into and say something misleading. So let me, okay. Very nice question, but let's not take that right now. Yeah.
So the Yang-Mills theory you are looking at in 4 dimensions, right?
Correct.
But you are reducing 10 dimension to 4 dimension in this case.
No. Okay.
Because
so what happened?
No, S5 in the other case.
No. Very good. Right. So it's the same physics, but it's described by theories living in different number of dimensions. Okay,
yes,
that's very
it
peculiar.
1 dimension, right?
But I'm not reducing. I'm not reducing.
Means it is described by surface Yang-Mills theory, but it's ADS5 is reduced into 4-dimension Yang-Mills, but there is like S5 there that we are not considering, right?
No. So the S5, the physics that happens on the S5, assuming it's not trivial in the sense of everything being smeared over the 5 sphere, the excitations of that are contained in this 4-dimensional theory. They're just not manifested by that theory living on higher dimensional spacetime, but rather by certain matter excitations within that theory. So this theory is highly supersymmetric. It has a bunch of fields. Amongst them, there are 6 scalar fields, and the scalars that mock up the physics in this sphere direction. So everything. So this really means not approximate or anything. This really means the full equivalence. And the very remarkable thing is that it manages to have this equivalence described by theories in different dimensions, which is certainly very counterintuitive. In fact, you might say it's preposterous. How can that possibly work? Okay, it's not obviously wrong because it's a strong weak coupling duality in the sense that if we want to have small coupling on the gravity side, small g, we're also stuck with having large lambda, which means it's very strongly coupled field theory. So our machinery, our toolkit for using, perturbative techniques goes out the window. And so, the intuition that you might have from standard field theory also has to be modified to provide for the thing being strongly coupled. So we don't even have natural description of, nice autonomous, degrees of freedom like particles and so forth propagating in this thing because the whole thing is very strongly coupled in the regime that it looks like gravity. Okay, so from that standpoint, okay, there is some hope that they are equivalent. In fact, people have tried, for the 2.5 decades since the original paper to shoot that correspondence down. In the 18,000 papers, most of them were sort of probably written with the hopes of saying, well, okay, there must be some regime where things just fail, because how can those be equivalent? And every time that test has been run with more and more sophistication, every time it came out miraculously the same. So you have a calculation on one side in gravity, and another calculation that looks nothing like it at any step of the way, completely different, and they give the same answer. And the answer need not be like a numerical thing. It can be, a complicated function of many parameters, many variables, which can look horrendous. It's in closed form, let's say, but nothing that, would be, some simple expression. And yet, the two things match. In some sense, it would be even more remarkable if somehow there wasn't a correspondence, because you would have all these coincidences which would be completely unexplained. So, but indeed, I very much sympathize if you feel queasy about how can that be true. I think that is that I agree with you. Okay, so let me just. Okay. Well, once you have it, okay, so once you have it in some basic form like this, you can now start deforming both sides. And so in particular, you can go away from the ADS asymptotics, for example, and so forth. So it goes beyond that. The original formulation starts from there, but once you have it, you can ignore string theory entirely, and just, well, or not entirely, but I mean, you can actually motivate the correspondence without recourse to string theory at all, and you can deform it such that you sort of relax various things. Okay, you can go to non-ADS, non-CFT, you can do this in various different dimensions, you can have other spaces here and so forth. So it's actually, if I say ADS CFT, or also known as gauge gravity duality, where the gauge refers to this side and gravity to that side, it really constitutes a vast, rich family of dualities, not just this single one that I have presented for you. Okay. So let me actually quickly, okay, 5 minutes. Maybe I'll leave the remarks for next time as a refresher, but let me, while I have those pictures, let me sort of tell you a little bit, maybe in, a posteriori motivation for why it's not so preposterous to expect that you might have such a correspondence. And that's sort of borrowed very much from this Horowitz and Polchinski review, which I think is very nice, which sort of starts by posit that, any sort of gauge theory will somehow contain a quantum gravity in it. But the sort of intuition is our expectation is as follows. So you have a, okay, it starts by thinking of the matter content. So you have a theory of gravity, okay, there's gravitons, and you have a gauge theory. Well, wouldn't it be nice if the spin 2 graviton can be thought of as a composite of two spin 1 gauge bosons? Well, by the Weinberg-Witten-Urgo theorem, we know that that can't happen when the things are propagating on the same Lorentzian spacetime. But already we know from holographic principle that gravity can live in higher dimensions and because it's holographic. And so you can think, okay, so the graviton would be propagating in higher dimensions. So the gauge theory somehow should contain not just secretly, not just the graviton, but also this extra dimension. Now for this extra dimension to be, physically interesting, it should be macroscopic. And well, physics should somehow be local with respect to some parameter that then could have a right of being thought of as some dimension. Okay, so what is a quantity with respect to which physics is local? One natural quantity is the energy scale, because the renormalization group equation is local in energy scale. Now, for that to be, well, and I also mentioned a moment ago that you want the gauge theory to be strongly coupled, because we know that the weakly coupled one looks nothing like gravity. So in order for that thing to remain strongly coupled over large energy scales, well, let's say we want it to be strongly coupled over infinite energy scales, well, so that motivates a CFT, a conformal field theory where the coupling does not run at all. Okay, so CFT, good, but what kind? Well, we want to be, generically, if theories are strongly coupled, they could be pretty badly pathological. Quantum, we don't know how to tame, the quantum fluctuations. So to our rescue comes supersymmetry to tame these quantum fluctuations. And so we want a supersymmetric CFT. And the simplest one is this one. Now, what type of a space will it live on? Well, we already have we would expect the 4-dimension Minkowski space, and now to that we add an extra dimension. That extra dimension should correspond to energy scale. And so for things to scale consistently, we expect the bulk metric to be something that has this flat Minkowski space. Let's say we have a new direction Z. So this one will have to be the most general metric we can write down with these symmetries will be something that has a 1 over z squared to get the right sort of scaling. So if I think of the UV of the theory, this would be at z equal to 0, and increasing the IR would be low energy scale. So the energy scale goes as 1 over z. And so we have motivated that the metric that we want is this happens to be, if you replace z by L squared over R, you get precisely the metric that we wrote somewhere, I guess out here, for just ADS5. Okay, so we have motivated already CFT and the ADS5, and if you probe this a little bit more, you have this maximal supersymmetry, so you want to promote the gravities to supergravity, and so you need a 10-dimensional solution for supergravity, and you eventually get to this, ADS5 goes S5. So that's a way of sort of motivating, and I should say, you can go further. You can even find sort of, excitations that have that sort of hark back to the string theory. We know that to get enough degrees of freedom in this lower dimensional theory to describe the physics of this 10-dimensional world, well, it has to have sufficient content in it. So we want a regime where you have large number of degrees of freedom. at some fixed lambda, so you want to take large n, so that's the so-called 't Hooft limit. And as 't Hooft argued, you can sort of repackage this as a string theory. So the string theory also sort of emerges in some sense from this very heuristic expectation. Okay, so next time, so maybe the remarks just to, oh, well, I'm over time, so I'll leave the remarks to next time. And what we'll do next time is to sort of start thinking about this ADS space-time, and then in the following lecture, what happens when you're just asymptotically ADS, and how can you build up the dictionary? Okay, so let me stop for today.